Preparing for a satellite systems engineering interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How do you approach turning mission objectives into a satellite system architecture? I start by translating mission objectives into measurable requirements: coverage, resolution, latency, lifetime, availability, and cost. Then I choose orbit, payload, bus sizing, ground segment, launch constraints, and operations concept. I keep margins visible for power, mass, data, thermal, and link performance. Finally, I verify the architecture through budgets, simulations, risk reviews, and test plans. The best designs trace every subsystem choice back to a mission requirement. While answering, focus on requirements flow down, mission objectives, orbit selection, payload needs, bus sizing, ground segment, constraints, trade studies, risk, margins, and verification planning. Question 2. How would you choose between LEO, MEO, GEO, and highly elliptical orbits for a mission? Orbit choice is a mission trade, not a preference. For Earth imaging, I usually favor LEO because it gives better resolution, lower link losses, and shorter latency, but it needs more satellites for persistent coverage. GEO is strong for communications and weather because one spacecraft sees a large region continuously. MEO fits navigation. Highly elliptical orbits help high-latitude coverage. I compare performance, radiation, propulsion needs, ground access, and total life cycle cost. Make sure to cover coverage, revisit time, latency, radiation environment, launch energy, ground station visibility, station keeping, payload resolution, mission lifetime, and cost trade-offs. Question 3. Walk me through how you would build a satellite communications link budget. A link budget proves the communication path closes with margin. I start with transmitter power, line losses, and antenna gain to calculate EIRP. Then I subtract free space path loss, atmospheric loss, polarization mismatch, pointing loss, and implementation losses. On the receive side, I include antenna gain, system noise temperature, GT, data rate, modulation, and coding. The final EBN0 or CN0 must exceed the required threshold with operational margin. In your answer, talk about EIRP, antenna gain, path loss, atmospheric losses, GT, EBN0, data rate, modulation, coding, implementation losses, and required link margin. Question 4. How do you size a satellite electrical power subsystem? I size power from an energy balance over the worst-case orbit. First, I list all loads by mode: payload operation, downlink, attitude control, heaters, avionics, and safe mode. Then I calculate solar array output with illumination, temperature, angle, aging, and degradation factors. Batteries must support eclipse and peak loads while respecting depth of discharge limits. I also include regulator efficiency and contingency margin. A good design survives worst-case eclipse without sacrificing battery life. Be sure to mention load analysis, solar array sizing, eclipse duration, battery depth of discharge, degradation, peak versus average power, power conditioning, margins, and safe mode loads. Question 5. What are the main components of an attitude determination and control system, and how do they work together? ADCS keeps the spacecraft pointed where the mission needs it. Sensors such as star trackers, sun sensors, gyros, magnetometers, and earth sensors estimate attitude. Actuators like reaction wheels, magnetotorquers, thrusters, or control moment gyros apply corrective torques. The flight software filters measurements, estimates state, and runs control laws against pointing requirements. I also account for disturbances from drag, solar pressure, gravity gradient, and magnetic torque, plus momentum dumping and safe mode recovery. While answering, cover sensors, actuators, estimation algorithms, control laws, pointing requirements, disturbance torques, reaction wheel management, magnetorquers, star trackers, and safe mode. Question 6. How would you design a satellite thermal control strategy? Thermal design keeps every component within allowable temperature limits across all mission cases. I model hot cases with maximum solar input and payload duty cycle, and cold cases with eclipse, low power, or safe mode. Passive controls include MLI, coatings, thermal straps, radiators, and conductive pads. Active controls use heaters and thermostats. I validate predictions with thermal vacuum testing. The trade-off is minimizing heater power while avoiding excessive thermal gradients. Make sure to cover hot and cold cases, thermal balance, conduction, radiation, heaters, radiators, MLI, coatings, orbital beta angle, component limits, and thermal testing. Question 7. What is TT&C? And why is it critical to spacecraft operations? TT&C stands for telemetry, tracking, and command, and it is the spacecraft's operational lifeline. Telemetry tells us health, mode, temperatures, voltages, and subsystem status. Tracking provides orbit determination through ranging, Doppler, or angles. Commanding lets operators configure the vehicle, upload timelines, and recover anomalies. I designed TT&C to be robust, lower rate, and highly reliable, often separate from the payload link. Security, command validation, and safe mode accessibility are essential. In your answer, talk about telemetry, tracking, command, health monitoring, command validation, ranging, uplink and downlink availability, encryption, safe mode, and operational procedures. Question 8. How do you manage interfaces between the payload and the satellite bus? Payload bus integration succeeds or fails at the interfaces. I define them early in an interface control document, covering mass properties, mounting, power, data rates, timing, thermal paths, fields of view, contamination limits, and electromagnetic compatibility. For example, an imager may drive pointing stability, data storage, thermal stability, and downlink capacity. I track every interface through reviews, tests, and configuration control. Ambiguous ownership is dangerous, so verification responsibility must be explicit. Be sure to mention mechanical, electrical, thermal, data, timing, software, contamination, pointing, EMC, ICDs, verification ownership, and requirements traceability between payload and bus teams. Question 9. What radiation effects must satellite engineers consider, and how can they be mitigated? Radiation risk depends strongly on orbit, lifetime, shielding, and component sensitivity. I look at total ionizing dose for long-term degradation, single-event upsets or latch-up from energetic particles, and displacement damage in sensors or solar cells. Mitigation includes radiation-tolerant parts, shielding, current limiting, watchdog timers, EDAC memory, redundancy, scrubbing, and safe software recovery. I avoid overshielding because mass rises quickly and secondary particles can matter. Testing and analysis must match the orbit environment. While answering, focus on total ionizing dose, single event effects, displacement damage, shielding, parts selection, redundancy, error correction, watchdogs, latch-up protection, orbit dependence, and testing. Question 10. How would you evaluate reliability and redundancy for a satellite subsystem? I begin by identifying mission-critical functions and single-point failures. Then I use FMEA, fault trees, or reliability block diagrams to estimate risk and consequence. Redundancy can be cold, warm, or hot, depending on response time, power budget, and failure modes. Cross-strapping improves flexibility, but adds complexity. Not everything deserves redundancy. Mass, power, and cost are limited. The goal is graceful degradation, where a failure reduces performance but does not immediately end the mission. Make sure to cover reliability block diagrams, FMEA, fault tree analysis, single-point failures, redundancy types, cross-strapping, graceful degradation, mission criticality, and mass power cost trade-offs. Question 11. What environmental tests would you plan before launching a satellite? Environmental testing proves the spacecraft can survive launch and operate in space. I plan vibration, acoustic, and shock tests for launch loads, thermal vacuum and thermal cycling for orbital conditions, EMI/EMC for compatibility, and deployment tests for mechanisms. Functional tests before, during, and after exposure catch workmanship or integration issues. The test level depends on qualification, acceptance, or proto-flight philosophy. I also protect against over-testing because test damage can be as real as flight damage. In your answer, talk about vibration, shock, acoustic, thermal vacuum, thermal cycling, EMI, EMC, deployment tests, functional tests, workmanship screening, proto-flight versus qualification, and acceptance levels. Question 12. How would you design the ground segment for a satellite mission? The ground segment must support operations, commanding, data delivery, and mission assurance. I start with contact analysis, station locations, elevation masks, link capacity, weather effects, and required latency. Then I design mission control, flight dynamics, telemetry processing, command approval, archiving, and payload data pipelines. For constellations, automation and scheduling become central. Security is non-negotiable for command paths. A strong ground design is tested with simulations before the spacecraft is ever launched. Be sure to mention ground stations, network availability, contact scheduling, mission control, data processing, latency, automation, security, orbit determination, commanding procedures, and scalability for constellations. Question 13. What factors influence propulsion system selection for a satellite? Propulsion selection starts with the delta-V budget. I include orbit raising, station keeping, collision avoidance, attitude maneuvers, momentum dumping, and end-of-life disposal. Chemical propulsion gives high thrust for fast maneuvers, but lower specific impulse. Electric propulsion is efficient and propellant-saving, but needs power and time. For small satellites, cold gas or green monopropellants may be practical. I also consider safety, contamination, thermal constraints, valve reliability, and launch provider handling rules. While answering, cover mission delta-V, orbit insertion, station keeping, attitude control, deorbiting, chemical versus electric propulsion, thrust, specific impulse, power, complexity, safety, and propellant storage. Question 14. A satellite suddenly stops responding to routine commands. How would you troubleshoot the anomaly? I would first avoid making the problem worse. I would confirm the ground system, antenna pointing, frequency, authentication, and command formatting before blaming the spacecraft. Then I would review last telemetry, mode state, power, thermal, attitude, fault logs, and recent command history. If available, I would use low-risk status requests or safe mode procedures. Recovery should follow approved anomaly plans, with one variable changed at a time. Discipline matters more than speed during spacecraft anomalies. Make sure to cover anomaly triage, last known telemetry, command history, ground system checks, safe mode, fault protection, power and thermal status, communication path, rollback, and disciplined procedures. Question 15. How do you address conjunction risk and end-of-life disposal for satellites? Conjunction management protects both the mission and the orbital environment. I monitor conjunction data, screen close approaches, estimate probability of collision, and evaluate maneuver options against fuel, operations impact, and tracking uncertainty. For LEO, I plan deorbit capability or compliance with disposal timelines. For GEO, I reserve propellant for graveyard orbit raising. End of life also includes passivation, venting pressure, disabling batteries safely, and reducing explosion risk. Responsible disposal must be designed in from day one. In your answer, talk about space situational awareness, conjunction data messages, probability of collision, maneuver planning, fuel reserves, passivation, deorbit rules, graveyard orbit, and debris mitigation. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.